Okay, so I suppose I'll get started. Uh, Good evening. Welcome to this problem solving and live interaction session for the subject experimental stress analysis. Today we will be discussing the contents from week 8, which has to do with photoelastic coatings. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics. My guide is Professor K. Ramesh, and my co-guide is Professor U. Saravanan from the Civil Engineering Department. So before we start, if there are any questions from what we have discussed till now previously, please feel free to ask. Or even if you have questions midway, you can feel more than welcome to ask them midway. Okay, so I suppose I'll move on to the first question of the day. To investigate regions of high stresses using reflection photoelasticity, the best practice to follow is which of the following? Apply a thick coating first to identify highly stressed regions, then paste a thin coating over the thick coating in the region of high stress. Or apply a thick coating first to identify the highly stressed region, then remove the thick coating and apply a thin coating in the identified zones. Or apply a thin coating first to identify the stress concentration regions, then paste a thick coating over this, or the other way around. That is, what they are trying to say is, let us say there is a specimen. I'm just drawing an arbitrary rectangle. It could be of any, or rather, let me not start with this. Let me say that my specimen is somewhat like that. Okay, so the idea is to find out what the high stress concentration zones are. So initially what they say is we will paste a thick photoelastic coating here, find out where the high concentration zones are. Let us say that this were to be the high concentration zone. Whether we would remove this and paste a thin coating there, whether they would remove this and paste a thin coating there, or paste it on top, or how to identify the stress concentration zone, whether that would be from thin or thick coatings. So essentially what we need to see here is the basic principle behind reflection photoelasticity. So if I were to say this is a variant of photoelasticity where we try to apply a photoelastic coating, essentially a birefringent coating, onto a specimen. Now the advantage is that we can analyze surface behavior for many material models. What I mean by that is we need not worry about whether the specimen material is isotropic or whether it is heterogeneous, homogeneous, composite, functionally graded. Only thing is limitation being that we can study only the surface behavior. But that being said, if we wish to study the surface behavior, we can always apply a isotropic photoelastic coating over it and study this. So the basic principle is the surface strain of the specimen is transmitted to the surface strain of the coating material. So for example, if there is a, let us say this is the specimen surface, and then we paste a coating, photoelastic coating material over this with the assumption that it is bonded properly and the adhesive holds, we take it that the surface strains from the specimen to the coating are faithfully transferred. And this is the basic principle behind which we try to develop the conceptual details. Now that the surface strain is transferred faithfully, our photoelastic coating is birefringent. So once it is strained, the stresses that will get reflected by appropriate optics. Now we know that for transmission photoelasticity, we had to have through and through, because the light was getting transmitted through the model. We could have the luxury of placing the light source behind the specimen, and the first and polarizer and the first quarter wave plate behind it impinge the light onto the model and then study it from the other side, thereby letting the light get transmitted. So this does not quite happen here, in which case we are constrained to have all the setup onto one side. So let us say that if this were the photoelastic coating that has been applied. So ideally speaking, as it was mentioned in the lecture, if I were to have a partially translucent mirror, and this will also pass the light, some of the impinging light that gets reflected off this mirror impinges onto the photoelastic coating with the model. Let us say that this is the model or the specimen, loaded specimen. So once the specimen is loaded, the surface strains are faithfully transmitted. So this will be developing fringes. How we can see those fringes are by having this kind of an optical arrangement, but this is very bulky and not possible always. So a variant of this is that we have somewhat of an oblique incidence. Let me just. So essentially we'll remove this. So we'll have light path like that. Let us say that it enters from here and then it exits from here. So this angle we call it let us call it alpha. So we will try to keep it as minimum as possible, since our photoelasticity's basic tenet is that it works on normal incidence. So we will not try to violate that too much, and then we have a polarizer quarter wave plate 1, and then we have another quarter wave plate 2 and analyzer 1, 2 and analyzer here. So we'll be having the light source here, and perhaps they view it from here, or we can use a digital camera here in order to capture the images onto image acquisition. So rest everything remains the same. If you see, what we have done is essentially the light source and the first polarizer and quarter wave plate, we have brought it to the same side, thereby introducing certain amount of error because of the oblique incidence, but nonetheless it is not appreciable. Now what is appreciable is the Poisson's ratio mismatch that comes between the specimen and the coating material, and the thickness of the material is also very sensitive, so we need to figure out how it is to be done. Anyway, from the basic principle, if we see, we have sigma 1 minus sigma 2 as nf sigma by T from the stress optic law. Similarly, we will have strain optic law. So epsilon 1c minus epsilon 2c, it will be given by nf epsilon by 2t. Why we have 2t is because essentially the denominator is not the thickness, but it is the length of the light path. Denominator represents length of the light path. So in case of transmission photoelasticity, it so happens to be the thickness straight away. Whereas in the case of reflection photoelasticity, we are able to see that once the light enters from here, if I were to just enlarge this portion, so we are able to see that light enters from here and exits. So it is traveling twice the distance, which happens to be the thickness of the photoelastic coating, which is why we take it to be twice the thickness. Okay, now having said that, we are able to see that for a given strain level, let me call this some constant, let me call this delta, or rather, let me pick some other alphabet. Let me call it constant K, capital constant K, not to be confused with the optical this thing strain. Let us say K strain is nothing but NF epsilon by 2T. So I'm able to see that n is n is directly proportional to my thickness or light path, or 2 times the thickness in this case. So the problem we have with reflection photoelasticity is that we do not have much discernible fringes. In order for us to have discernible fringes, we would want a higher optical response. How can we have higher optical response? Based on the thickness? The thicker the specimen, the thicker the coating, higher will be its optical response. But the thicker the coating, there will be other issues that will start coming in, because the thickness of the coating, as we increase it, it should not start reinforcing the material or the specimen material itself. So there is a trade-off between reinforcement provided by the coating and the optical response that is needed. And there are certain other considerations that we need to account for, uh, that come as correction factors. So this is what is wanted. Now, if we were to approach this problem, let us say that we have a trade-off between coating, reinforcement effect, and high optical response. So this implies that thickness should be very less, and for this thickness should be high. So essentially, a workaround here is that first we will apply it to a specimen. We will apply a thick coating to a specimen, and because of the thickness, optical response will be high, in which case we can easily identify which are the stressed regions. Now, the other option says that we will paste a thin film over the thick coating, which is nothing but increasing the thickness of the coating further. So this will be detrimental. So definitely A and C don't apply here. So naturally we need to remove the coating and then repaste it. So first, if we have high optical response, we will be able to identify the stress concentration, highly stressed regions first. Upon arriving at that information, we will be removing the thick coating and then replacing it with the thin coating, so as to minimize the coating reinforcement effect and study the problem faithfully. So essentially, we will first apply a thick coating to identify the highly stressed region, then remove the thick coating and apply a thin coating in the identified zones. So this is the way to go about. So I hope that this is clear. If there are any questions, please feel free to ask midway. So yes, okay. But anyway, I will be providing this PDF I'm uploading week-wise. So you can check it from there also in case you missed something, in case you feel that you missed something. So can I move on? Yeah. Okay. So let us look at this question. The assumption made for comparing the stresses developed on the coating and specimen in reflection photoelasticity is which of the following, or which of are, that is one or maybe more options. So the coating thickness is smaller as compared to the specimen thickness. We just saw that if coating thickness is comparable, is equal to the specimen thickness, then we have reinforcement reinforcement effect that is coming in. So there is no question of having a coating thickness that is more than the specimen thickness, which will anyway defeat the purpose. So our fundamental assumption is that the coating thickness is much smaller compared to the specimen thickness. This is definitely there. And because in order to avoid the mismatch that comes about, we take it that the Poisson's ratio of the coating mu c is same as mu s. So we will see cases where this assumption might not be uh, very prudent to make, but regardless, we first start with this basic assumption that we take the Poisson's ratio of the coating to be same as the Poisson's ratio of the specimen. So the coating and specimen are in a case state of plane strain. This is not correct because we essentially take the coating and the specimen to be in the state of plane stress, and that is how we derive the equations which we will be seeing. So this is comes within the derivations of strain optics law, so to speak. So these are the two assumptions that we proceed with for comparing stresses developed in the coating and specimen in case of reflection photoelasticity. So I hope that this is clear. So let us look at the next question. When photoelastic coating with finite thickness is applied over beams and plates, correction factors are necessary because of which all effects essentially is what is being asked. So let us say that we have a beam and that it is loaded. Let us say that it's a 4-point bend beam. So essentially we will have the beam bent like that. So if we were to apply the photoelastic coating here, let us say, if we were to apply the photoelastic coating here, we know that the strain variation is linear in this case. This is for the beam section alone. Inside of the beam section, we know that strain variation is linear. E in the specimen. So I take this as the specimen and let me call this the coating. So inside of the coating, if we see, I'm just detaching it to make it clear. Okay, let me not do that. I'll just take the coating to be like that. Sorry, 1 minute. Yeah, if the coating were like that, and under the assumption that it is bonded properly, my strain would vary inside the coating also. In which case, from the back end of the coating to the front end, there is a variation of strain, which needs to be accounted for. So, with this background, if we were to see this, specimen reinforcement due to coating has to be considered. There exists a strain gradient in the direction perpendicular to the surface. So, this is the surface. This is the direction perpendicular to the surface. So, there exists a strain gradient in the direction. Strain variation over the thickness is zero. If strain variation over the thickness was zero, it implies there is no strain. Or rather, if we were to focus too much on the word variation, we could even say that with a constant offset, there is no variation but a single value, which happens only in the case of a uniaxial loading case. So that also doesn't seem to be the case here. Fringes observed are proportional to the surface strain. This is true that fringes observed are proportional to the surface strain, but we need not do make any correction factors for this. This is a phenomena based on which we are essentially hinging our entire analysis, but that is not anything that involves correction factors essentially. So specimen reinforcement due to the coating has to be considered. Yes, this is true. This has to be considered. Only thing is, if we have very thin coating, then we need not, this can comfortably be ignored. But since we have qualified in the question that we have coatings with finite thickness, essentially these need to be considered. So I hope that this is clear. So if there are any questions, please feel free to ask. Next, I'll move on to the next question. I'll just mark this as epsilon coating varies linearly. And this is the actual section. Let me put it here. Yeah. Okay. So let us look at the next question. John wanted to measure the stress concentration factor near a bolt hole in a copper plate used in a heat exchanger. An epoxy coating is applied over the plate of length 150 mm with a hole diameter of 8 mm. So essentially what we have here is we have a plate with a hole. The hole dia is given to be 8 mm dia and the plate size is given to be 150. Okay. So the Poisson's ratio of copper and epoxy are 0.3 and 0.36 respectively. So essentially this is made of copper, which has a Poisson's ratio of 0.3. So what we have is mu specimen is 0.3 and the coating is epoxy. So if we were to see the cross section here, what has been done is I don't know what is the issue. Okay, never mind. I'll just draw it like that. So we have our specimen here. This is the hole. Yeah. Yes. Yeah. What? Okay. So the coating has been applied here. So mu C is given to be 0.36. Okay. As the plate is subjected to a tensile load of 600 Newton, the far field fringe order on the coating was found to be 1.57. So when this was loaded with a load of 600 Newton, stress somewhere at the far field fringe order was found to be 1.57 in the coating is what it is given. And the maximum fringe order at the boundary of the hole was found to be 3.06. So essentially at this point, if we were to see here, the stresses will shoot up and N at the boundary was found to be 3.06 is what is given. So answer the following questions based on this. What is the stress concentration factor if the Poisson's ratio mismatch is neglected? Essentially, this mismatch that is coming 0.3 to 0.36. If it is neglected, what will be the stress concentration factor is what is asked. So we know that stress concentration factor is nothing but N maximum upon N far field. If we were to ignore the Poisson's ratio mismatch in case of photoelastic coating. So this would be nothing but 3.06 by 1.57. So this will come out to be 3.06 by 1.57. This comes out to be 1.95. Around 1.95 is our SCF when we ignore the Poisson's ratio mismatch. And what is the stress concentration factor if the Poisson's ratio mismatch is taken into consideration? In such a case, it is also given in the lecture that this would be defined by N far field into 1 plus mu s upon 1 plus mu c. So if that be the case, we already know that this quantity is nothing but 1.95. It is 1.95 into 1 plus 0.3 by 1 plus 0.36. So this comes out to be 1.3 by 1. Comes out to be 1.86. Okay. So based on this, it is asked, is it advisable to neglect the Poisson's ratio mismatch in the data interpretation? So what we see is SCF when we mu s when there is no mismatch is greater than SCF with mismatch that is considered. So in such a case, what is it that we should do? Essentially, this is leading to a, if we ignore it, what we are doing is we are overestimating the SCF. Hence, it is advisable that Poisson's ratio mismatch has to be considered in the SCF evaluation for reasonable evaluation of our stress concentration factor. So I hope that this is clear. So if there are any questions, please do ask. Okay, so I take it that this is clear. So let us look at this problem. A tractor tire needs to be studied using photoelastic coating technique for the stresses developed. So we are dealing essentially with rubber-like material. So Mithila selected a suitable coating material from the list given below. The calibration was done with a 2 thick tension specimen made of the coating material. So he selected a coating material and took a 2 thick tension specimen out of that coating material and did transmission photoelasticity under white light with lambda equal to 577 nanometers. The calibration specimen has a width of 30 and a length of 70 So let me just draw that. Okay, so we have this as 30 this is 70 and its thickness, out of plane thickness is 2 is what is given. During that calibration, a fringe order of 3.5 was observed at a particular point. At some point, since this is in uniaxial tension, so it doesn't matter where we see sufficiently far away from the edges. Let us just take this point, and here fringe order is found to be 3.5 when the corresponding load was 600 Newton. So let me just move this here. This 600 Newton was applied. Okay, so with this, we have some data given here in this table. So for the material polycarbonate, EC and mu C is given. Similarly, for epoxy, PS3 and polyurethane is given. So which is the suitable coating material for the analysis is what we are asked. So what we need to understand here is that we are dealing with rubber, which in itself is a soft material. In which case, if we were to have our uh, Young's modulus of the coating material comparable with the rubber, then it would lead to reinforcement effects. So these three, if we see the first three, reinforcement effect would be significant. Because if we were to see the polycarbonate, epoxy and PS3, they have essentially not PS3 so much, but polycarbonate and epoxy definitely have much higher stiffness, and this would essentially reinforce the rubber. So whatever phenomena we are trying to study, it will throw off the results. So the viable candidates seem to be PS3 and polyurethane, out of which polyurethane happens to be very, very soft, much softer, way softer than rubber, in which case polycarbonate would be the ideal choice for a photoelastic coating material. Okay, so determine the material stress fringe value. So we are given this is a case of uniaxial tension. Load is 600 newtons distributed over an area of, this is 30 wide and 2 thick. So if we see sigma 1, which is nothing but our maximum uniaxial tension, is 600 by 30 into 2. This is nothing but 10 MPa. Sigma 2, if we see, is 0 for the case of uniaxial tension. So sigma 1 minus sigma 2, we know it is 10 MPa, and we know it is N F sigma by T. Why not 2T? Because we are doing this using transmission photoelasticity. So a light path is only equal to only one factored by 1, the thickness factored by 1. So if we were to see this, let me just go to a new page. Okay, so that being the case, 10 is, we know that fringe order observed was 3.5. In which case, I'll just move this over here. So fringe order observed was 3.5 into F sigma by thickness is 2. So what our F sigma comes out to be 20 by 3.5, which is nothing but 5.714 Newton per mm per fringe. So this we have got it to be 5.714. This is our F sigma. Now the material strain fringe value is what is asked. So let us see how to derive this. Okay. So in case of with the assumption of plane stress for coating, E1 of coating is nothing but sigma 1 of coating by E coating minus mu C sigma 2 C by EC. The third stress is 0. Similarly, we have E2C is sigma 2C by EC minus mu C sigma 1C by EC. So here, if epsilon 1C minus epsilon 2C we were to take, EC minus mu C sigma 2C by minus sigma 2C by EC plus mu C sigma 2 sigma 1. We get this relation. It is nothing but, if we take it to be common, sigma 1C into 1 plus mu C by EC minus sigma 2C into 1 plus mu C by EC. So this results in epsilon 1C minus epsilon 2C is nothing but 1 plus mu C by epsilon C into sigma 1C minus sigma 2C. So far so good. Now we know that this can be replaced by this thing can be replaced by NF epsilon by T, and this can be replaced by NF sigma by T. So what we essentially see is F epsilon is 1 plus mu C by EC into F sigma. So this is the relation between material stress fringe value and material strain fringe value. So in cases where we are not able to find out F epsilon, we would resort to finding F sigma by a simple tension uh, test as we did here, and then back calculate F epsilon. So this is the material stress strain fringe value relation. So now for our problem, we know that F sigma, yeah, from our problem, we know that F sigma is 5.714. So F epsilon is nothing but 1 plus mu c by EC into 20 by 3.5 is what we got, which is 5.714, which is 1 point. What is mu c? So we have selected polyurethane. So essentially our mu c is 0.5, EC is 0.004 GPa. So if we were to use that here, we will get 1.5 upon 0.004 E3, because we are expressing it in Newton and mm, into 20 by 3.5, or F sigma, F epsilon, I'm sorry, F epsilon comes out to be into 1.5 upon, so this comes out to be 2.143. And what are the units for this? We can just see from this expression itself. So if we were to take the dimensions, this is somewhat aside. So the dimensions for this Poisson's ratio is a dimensionless quantity. So 1 by E dimension is, let me just simply write the units rather, Newton per mm square into F sigma's unit is Newton per mm per fringe. So essentially we are seeing that it is mm per fringe. So this is mm per fringe. Yes, any questions, sir? Where? Yeah, yes. Why we got n? This n you mean? Yeah. No, no, this is not. I wrote or. I'm sorry, I should have written it properly. I hope that is clear. Yeah, yeah. So F epsilon is nothing but 2.143 mm per fringe. This is the unit. Mm per fringe. So we have calculated F sigma, we have calculated F epsilon here, 2.143. So F epsilon is, now we have been asked the strain optic coefficient is dash into 10 power minus 4 fringe. So essentially our strain optic coefficient F epsilon, if we see, it is nothing but lambda by K. Similarly, F sigma is lambda by C, as we saw when we were developing. So this strain optic coefficient is what is asked. So we know that K is nothing but lambda by F sigma. If we were to see the units, lambda is length, the dimension is length, and this is length per fringe. Fringe, essentially, this is a very crude way to write. Fringe is not any SI dimension. I'm just trying to emphasize the point that this will come out to be fringe. So mm per fringe. So this will just cancel out. Okay, so K we know is lambda by F epsilon. So lambda from the question it is given that our lambda is 577 nanometers is given. So let us substitute that is 577 into 10 power minus 9 meters into 10 power 3 millimeters. Since our F epsilon is in millimeter per fringe, this divided by 2.143 is what we have to evaluate. So this comes out to be 577 to 10 power minus 6 upon 143. This comes out to be 2.69 into 10 power minus 4. So we need not account for this 10 power minus 4 since that is already given in the question. So we just report the value that we have got. So I hope that this is clear. So if there are any questions, please feel free to ask. Okay, so let me take a look at this problem. But before we do, I'll just digress a little bit and try to develop the stress coating stress to specimen stress relation is something we should clearly understand. So under the assumption of plane stress, we know that coating stress so under the assumption of plane stress, epsilon 1c for the coating is nothing but sigma 1c by EC minus mu c sigma 2c by EC. Similarly, epsilon 2c is sigma 2c by EC minus mu c sigma 1c by EC. So this is for the coating. Similarly, if I were to say yeah, whether it is no brittle coating we have not reached yet. That will be coming next week. We are still in photoelastic coating only, but the same relations apply essentially if you see. Okay, yeah. So for specimen, we have E1 specimen is sigma 1 s by Es minus mu s sigma 2 s by Es. Similarly, E2S will be sigma 2 by minus mu s sigma 1 s by Es. Okay. Now this was under the plane stress assumption. Yes, sir. Uh, yeah, because it is in nanometers. Uh, yeah, it is in meters, no? Te- See, lambda is 577 nanometers. Nanometers, which is 577 into 10 power minus 9 meters. But since our F epsilon is in mm, we need to convert the numerator also to mm. Hence, multiplying it by 1000. Okay, yeah. Okay, so here first initially we considered the plane stress assumption and got this. Now if we were to consider, we consider that the adhesive that is holding the photoelastic coating onto the specimen faithfully transmits the strains, in which case epsilon 1c is equal to epsilon 1s and epsilon 2c is equal to epsilon 2s. So from this relation we can see what we are trying to essentially say is this is equal to this, and this quantity is equal to this quantity. So now if we were to essentially eliminate uh, one of the quantities, then we will be getting the other in terms of this. So from the first equation, let me write it this way. Let me put it here. A is, where is A? ES and EA. Where is EA, sir? ES is not in the problem discussion. Okay. S is specimen. A, I'm not sure what, if it is given in the problem that the specimen is aluminum. No, we cannot make, see, when we are talking in context of a photoelastic specimen, then S is reserved for specimen, C will be reserved for coating. If we are very problem specific, then ES could may well be steel. Why should it be specimen if A is aluminum? So if this happens to be a doubt, then this should be clarified before attempting the question, because this ambiguity is important to resolve before we approach the problem. Yeah, all right. So for this discussion, EC is all subscript C is for coating and subscript S is for specimen, unless otherwise specified, of course. So please keep this in mind. So if I'll just move this here. So we have got two equations. Just trying to emphasize on how we got the strain uh, that is stresses from the coating related to stresses to the specimen. How we are trying to get that. So from here, if I see this, sigma 1c is, okay, why don't I add this? Let me call this, I'll put this here itself. This is 1, this is 2. Now 1, if eliminating sigma 2c, for eliminating sigma 2c, 1 plus mu c into 2 is what I need to do. So if I were to write that out, sigma 1c by EC minus mu c sigma 2c by EC plus mu c sigma 2c by EC minus mu c squared sigma 1c by EC. I'll be getting this straight away, and I'll be getting this with mu c additionally. So these cancel out. So if I see sigma 1 c into 1 minus mu c squared upon EC, if I were to take something common from that side, it will be 1 by ES. Okay, so this is sigma 1s into 1 minus mu s mu c minus, or rather plus, sigma 2s into mu c minus mu s. Okay, so this gives us the expression sigma 1c is nothing but Es upon Ec into 1 minus mu c whole square into this expression. So we have got sigma 1 c in terms of sigma 2 s, sigma 1 and sigma 2 s. So this is one of the equation. So similarly, when we let us say we substituted from 1 and 2, instead of eliminating sigma 2c, if we were to eliminate sigma 1c, we will get sigma 2c is Es upon into 1 minus mu c squared. So the positions will just flip, 1 minus mu s mu c plus sigma 1 s into mu c minus mu s. So this is what you will essentially get. Why don't I? These are the two relations we will get. Now, if I were to see sigma 1c minus sigma 2c, if I were to take this, then essentially what I would get is this, and within my bracket, I'll get sigma 1 s into 1 minus mu s mu c. This and this will get subtracted. This will get subtracted from that. So I'll just pull that out and write it as common, minus mu s minus mu c plus mu s. Okay. Plus sigma 2s into mu c minus mu s minus 1 plus mu s mu c. If I subtract these out, this is the expression I will get. So once I have this, I can just open this up and simplify. Es upon Ec into 1 minus mu c the whole square. I'm sorry, this needs to be taken care of. Since Ec is at the denominator here, so this ratio will just be the opposite. Ec by Es. Since Es is at the denominator here, it will be maintained in the denominator. I hope that that is clear. So I'll just maintain it. Es, Ec, Es. Okay. Rest of the thing is fine. Sigma 1 S into. Now if I were to write this out, this will be 1 minus mu S if I take common, 1 plus mu S. And since we are subtracting this out, yeah, so plus sigma 2S into minus, yeah, so 1 minus will come out here. And this will be 1 minus mu S into 1 plus mu S. This will be the term inside the bracket. Now having done this, we can simplify further. Sigma 1c minus sigma 2c is nothing but Ec by Es into 1 minus mu c squared into 1 minus mu s into 1 minus 1 plus mu c. This will be 1 minus mu c. Okay. Into sigma 1s minus sigma 2s. So which implies sigma 1c minus sigma 2c is into this. So we can see from here that these cancel out. There will be 1 plus actually 1, 1, 1 plus mu s. So plus mu s. So this will come out to be plus. Because I remembered the end result, that is why. I hope that you can follow once you look at the derivation closely. I suppose you'll be able to follow that. Sigma 2c is nothing but Ec upon Es into 1 plus mu s upon 1 plus mu c into sigma 1s minus sigma 2s. If I were to invert it, because sigma 1s minus sigma 2s is what I'm trying to study. That is the principal stress difference in the specimen is what I'm trying to study. So sigma 1s minus sigma 2s is nothing but Es into 1 plus mu s Ec into 1 plus mu c into sigma 1c minus sigma 2c. This is how we relate our specimen stresses to our coating stresses to specimen stresses. Now that we have done that, we have another relation, that sigma 1c for the coating we have sigma 1c minus sigma 2c is nf epsilon, or rather nf sigma by T. If I were to replace this with strain components, then I would be getting essentially twice this. So let me just do that. So I'll be having twice the thickness into 1 plus mu c. So let me, if I were to substitute that back, I'll get sigma 1s minus sigma 2s is Es upon 1 plus mu s into Ec mu c, and we have this here Nf epsilon Ec upon 2t into 1 plus mu c. I can see that these things will cancel out. And writing, and since f epsilon is nothing but lambda by k, I write sigma 1s minus sigma 2s as Es upon 1 plus mu s into n by 2t into lambda by k. This is our grand expression that we get towards the end. So once we know k, we know the thickness. Once we know the specimen material properties, the fringe order with a given light wavelength, we can relate the fringe orders to the specimen stresses directly. So I hope that this is clear. I took a little bit of digression because it was just, I thought it will be valuable to explain this once derivation in detail. Okay, now this is for an ideal case. When we have our reinforcing effect that is taking place because of the coating onto the specimen, then we also need to account for the correction factors, in which case sigma 1s minus sigma 2s will be related by one reinforcement factor into Es upon 1 plus mu s into n by 2t into lambda by k. This is what we'll be using. Okay, so this is relating using photoelastic coating. Coatings. So I hope that that is clear. So anyway, let us look at the question now. Enough of that digression. So a general purpose aluminum ladder has a life of about 15 to 18 years if a good grade of material is used. As part of estimating the ladder's life, Naveen conducted a photoelastic coating experiment on the aluminum bar. Okay. For the vertical support members, that is side rail, essentially we have a ladder which has rungs in between. So we know that these rungs will be subjected to bending, and these axial, if I were to select this, or rather let me choose some other color. We know that these will be subjected to axial forces. Axial compression, and essentially this will be subjected to bending. Okay. So what I said is Naveen conducted a photoelastic experiment on an aluminum bar. For vertical support members, the side rails, he conducted an axial load test. And for the horizontal members, the steps or the rungs as they are called, a bending test is conducted. The properties of the specimen and coating are given in the table below. The same specimen dimensions are used for both the experiments. Okay. So the white light lambda is given to be 577. Should be noted that white light is a distribution of wavelength. So essentially, we try to take the mean of that, which comes to around 577 nanometers. Is used for the illumination, and strain optic coefficient K is given to be 0.12. Neglecting the Poisson's ratio mismatch, answer the following question. So we've been asked to neglect the Poisson's ratio mismatch here. Okay. So with this slide, let us look at the question. So the first part says the correction factor required in the case of axial loading is, so some we'll just populate the data first. So whatever the given data is, it says specimen or the specimen thickness is 4 mm and the coating thickness is 1.5 mm. K is given to be 0.12. Then E of the specimen is 71 GPa. E of the coating is 3.3 GPa. Poisson's ratio of coating, or rather the specimen, is 0.33. Poisson's ratio of the coating is 0.37. So this is given. Okay. So first we need to calculate the correction factor required in the case of axial loading. So let us see what it is. Correction factor in the case of axial loading is given by, it is given in the lecture in detail. So one can also find this in the data sheet. So it is given by 1 plus HC by HS into EC by ES into 1 plus mu S 1 plus mu C. How this is arrived at is essentially we will take an uncoated specimen. We'll take an uncoated specimen and then we'll take a coated specimen where this is taken to be the coating and this is the specimen and this is uncoated specimen, and we'll apply the same load and try to do the force balance. Whatever comes out to be the ratio is what is shown as the correction factor in the case of axial loading. So which comes out to be this, which is derived in detail in the lecture. So I'll just go ahead and plug in what is needed. So HC we saw is 1.5 by 4 into EC by ES into 1 plus 0.3, or rather 1.33, 1.33 by 1.37 is our correction factor. So what does this come out to be? 4 into 71 into 1.37. So this comes out to be nearly 1.02, 1.0619, which is close to 1.02. So we can see that it gives a variation of 2%, which is not much, but nonetheless, if we are to account for it, we have to account for it. Okay. So we have this now. This is 1.02. We've got this to be 1.02, which is nothing but RA. Now the fringe order observed for a tensile load of 2.4 kilonewton is what is asked. So we know that the axial load case, the side rails is what it was called. Side rail is subjected to uniaxial compression. in which case sigma 1 will be 0, sigma 2 will be minus, what was the load? Okay, so since this was being tested, we have applied a tensile load, in which case my sigma 1 will be stress that was applied, that is load is 2400 kilonewton by my cross sectional area. In the question, the cross sectional dimensions are given. So length, width and height. So I can see width and height makes up my cross sectional area. So 6 into 4 in mm. This comes out to be 2.4E3 upon 24. 2.4 kilonewton, right? 2.4 kilonewton upon 4 into 6 is 100 MPa. Sigma 2 is 0 since we are applying only tension. So sigma 1 minus sigma 2 is NF. Since we are doing it with photoelastic coating, so we know that these are specimen stresses. So this will come as we derived it here. This is what we have to use here. So let us put it in place. Except that T will be replaced by HC now. Okay, so what does this come out to be? Sigma 100. This will essentially be 100 minus 0 is, or 100. 100 MPa is, what was the correction factor we got? 1.02 into ES. ES is 71 GPa upon 1.33. 1 plus mu is into N by 2 into HC. HC is 1.5 into lambda. I'm straight away writing it in mm rather than meters and then converting it back. And K is in the question, it is given to be 0.12. So from here, I can back calculate N. Let's do that. 77 minus 6, right? So I get 1.15. This is my fringe order that I'll observe. So I'm able to see that fringe, as opposed to transmission photoelasticity, it shows much less fringe order for a considerable load of considerable stress of 100 MPa. This is one of the demerits of one of the drawbacks one can say of using photoelastic coatings, in which case we need to amplify the optical response by some other means. Okay, so the next question, as this is N observed, is 1.15. The distance of the neutral axis from the bottom of the bending specimen. Essentially, now the side rail is done. Now we have the steps, which where the bending load was applied. So we are asked what is the distance of the neutral axis in mm from the bottom of the specimen. So we know shift of the neutral axis, or rather distance I should say, accounting for the shift, distance of the neutral axis is given by this EC by ES, HC by HS. So the idea is to plug and at least reflect on the results as to what they are trying to convey, because we are not just trying to evaluate this for no reason. HC by HS whole square. So this is what it comes to. So the shift, so the distance would be HS. HS we know is 4 mm by 2 into 1 minus EC. EC is 3.3, 3 by 71 into 1.5 by 4 whole square divided by 1 plus this thing. So does this come out to be 3.3 into 1.5 square divided by 71 into 4 square into 4.2. So this is around 1.97 mm, as opposed to being exactly at half the distance, which would have been the case. We can see that the neutral axis gets shifted. So this is essentially from the top. So we know that from the bottom face it will be thickness minus this thing. It comes out to be 2.03 mm. The correction factor required in the case of bending is asked. Again, it's plug and evaluate. Correction factor for the case of bending is given by a big expression where, let us say, E is EC by ES and G is our HC by HS, and this will be in terms of this. So the correction factor required for bending is given by 1 plus EG upon 1 plus G into 4 into 1 plus EG cube minus 3 into EG squared, the whole squared, by 1 plus EG, the entire thing multiplied by 1 plus mu s upon 1 plus mu c. I understand that it's a little dry because we are just plugging and uh, getting the results, but the important point is to evaluate and then reflect back on the results as to what we are getting and what it indicates. So let us calculate ES first. ES is 3.3 by 71 and GS this is nothing but 0.046. G is 1.5 by 4, which is 0.375. By substituting, we'll be getting 3.3 by 71, 1.5 by 4. Okay, 1 plus EG upon 1 plus G into 1 point. Mu C is, the question it is given, it is 1.37, 0.37. 4 into 1 plus E into G cube into 1 minus E into G squared whole squared divided by 1 plus E into G. So this comes out to be 0.789, 0.79 exactly. So what this tells us is our optical response needs to be, it is amplified, so we need to reduce it in order to get the actual effect. Reduce it by say 80%. So RF in bending is 0.789. So the principal stress difference in the specimen due to bending if the fringe order observed in the coating is 2.05. So, okay. So essentially we know that this thing holds. Okay, so we know this is 0. Maximum fringe order is what is given. Or the principal stress difference is asked. 1 minute. Let me go back to the question. The principal stress difference in MPA is asked. The specimen due to bending is observed to have a fringe order of 2.05. So n is 2.05. So essentially this will be 0.789 into 71 E3 by 1.33 into 2.045 upon 2 into 1.5 into 577 by 0.12. So the principal stress difference in the specimen. This will come out to be 168. Okay, let me. So this comes around 168.77 MPa. So you can also parallelly check the calculations if everything is holding fine. Oh, sorry. Okay, this was the issue. Actually, fringe order is not 2.5, but it is 2.05. So essentially, it won't be 2.5. Yeah, so my stress would be 138. 0.39 MPa. So I hope that this is clear. So the principal stress difference comes out to be 138 or close to 138.4 MPa. So this is how we need to address this. So we saw that correction factors are sometimes giving some amplification or reduction. So this is essential to account for in the case of using contourable plastics, because otherwise our results will not be reliable. So I hope that this is clear. So anyway, I have run out of questions. So if there are any questions at this point, I encourage you to please ask. Is are there any questions based on what we discussed? Is everything clear? Okay. So I take it that the things we have discussed is clear. So if there are still any questions, I'm happy to take them. Otherwise, I'll call it a day because I've run out of questions. So I hope that I've done some justice to the derivations and trying to explain how photoelastic coatings are used and what are the merits and demerits, or I, rather than demerits, what are the limitations which we should keep in mind, and in selecting the thickness and selecting the material, and how it could be problematic if we do not account for the correction factors, and as opposed to an ideal case when correction factors are used, how the results come out to be. So if it is clear and if there are no questions, I'd like to call it a day and end the session now. Okay. So thanks. Thank you for attending. I'll see you next week.